Hello! This will be a demonstration of Proposition 8 from Book 9 of Euclid's Elements, which says that if numbers be in continued proportion beginning from the unit, the third from the unit is a square number, and so are all successive numbers which leave out 1. The fourth number from the unit is cube, as are all successive numbers which leave out 2. And the seventh number is at once both cube and square, as are all successive numbers which leave out 5. This is a big proposition, a very important one, but also a very confusing one. So let's break it down. We're going to have 6 numbers, A, B, C, D, E, and F. They will be continually proportional starting from the unit. What that'll mean is that the unit is to A, just as A is to B, just as B is to C, just as C is to D, just as D is to E, and just as E is to F. So the unit all the way up until F form a continued proportion. What we want to prove about this continued proportion is that the third number is square, the fourth number is cube, and the seventh number is both square and cube. We're also going to prove this for all numbers which leave out 1, which leave out 2, and which leave out 5, respectively. What that means for us in particular is that our third number, B, will be square, as are all successive numbers which leave out 1. Our fourth number, C, will be cube, as are all successive numbers which leave out 2. And our seventh number, F, will be both square and cube, as are all successive numbers which leave out 5. Now, you might already be asking yourself, as I did when I first got to this proposition, what does leaving out 1 or leaving out 2 or leaving out 5 mean? Well, it means skipping is how we would say that nowadays, or we would leave an interval of 1 number, 2 number, or 5 numbers between each square and the next, or each cube and the next, or each square and cube to each square and cube. It's kind of a confusing way to word it, but I'll break it down here. So our third number, B, is a square number. We also want to prove that all successive numbers which leave out 1 are also square. What that means is we're going to skip one number, and the number we land on, which will be D here because we skipped over the one number C, number D will be square as well, and we can go from D, skip E, skip the one number E, land on F. F will also be square. That's what we're going to prove. And likewise, we start at C. C is our first cube. We skip over 2 numbers, D and E. We land on F. F will also be cube, and we can keep doing this. So the language about leaving out 1 or 2 or 5 is that between the consecutive squares or cubes, or squares and cubes, those kinds of numbers, there will be one number between each consecutive square, there will be 2 numbers between each consecutive cube, and there will be 5 numbers between each consecutive square and cube number. With that said, let's begin by proving this. We know that the unit is to A, just as A is to B. We were given that the unit A and B form a continued proportion. And we know the unit measures A. So we can also say, just by the definition of proportionality, that A measures B the same number of times that the unit measures A. But then this means, by the definition of multiplication, that A times A makes B. Or in other words, that B is equal to A squared, which means, of course, that B is a square number with sides of A. We also know that B, C, and D form a continued proportion. B is to C just as C is to D. We were given that. And we know from Proposition 8.22 that when 3 numbers are continually proportional, and the first is square, the third is also square. So that because B, C, and D are 3 numbers in a continued proportion, and the first of them, B, is square, the third of them, D, is also a square number. And in just the same way, we can prove that the number F is also a square number because D, E, and F form another continued proportion, and by another use of Proposition 8.23, because the first number D is square, the third number F is also square. And we can do this for all numbers, all successive numbers which leave out 1. So if we were to continue this proportion, the next square would be H with G in between F and H, then it would be L, then it would be N, and so on and so forth. All consecutive square numbers in our continued proportion beginning from the unit have 1 number between them. Next, we know that the unit is to A, just as B is to C. We were also given that in our continued proportion. And we know that the unit measures the number a, just by definition of being the unit, which then means by definition 720, the definition of proportionality. Because the unit is to a just as b is to c, the unit measures a the same number of times that b measures c. But this also means by the definition of multiplication, definition 715, that a times b makes c. We also know, we had also shown in our first step, that b is equal to a squared. So a times b is really just a times a squared, or in other words, a cubed. And that makes the number c. So a cubed is c. That c is a cube number, this is obvious, with side lengths a. So c, cube number, the sides are a. We also know that the four numbers c, d, e, and f form a continued proportion. We were given that as well. And we know from proposition 823 that if four numbers are continually proportional, and the first is cube, the fourth will also be cube. So that because c, d, e, and f form a continued proportion, and the first number c is a cube, the fourth number f is also a cube. But we've also shown that the number f is a square number, and so our seventh number f is both square, as was shown in our second step, and cube, as shown in our fifth step. Now, similarly to how we prove that c and f are cube numbers, we can prove that all successive numbers which leave out 2 are cube numbers as well. So if we were to continue this proportion in alphabetical order, we would have the cube numbers of c, f, the next one would be k, leaving the two numbers g and h between them. Then after k, it would be n again. No, would it be n? K, L, M. No, it would be n. Yeah, n. Leaving between k and n, l and m, and so on and so forth. So we can prove that all consecutive cube numbers in our continued proportion beginning from the unit are two numbers apart. Now, in just the same way that we prove that the number f is both square and cube, we can also prove that all successive numbers which leave out 5 are also both square and cube. So again, if we were to continue this proportion in alphabetical order, it would go f, we would skip over g, h, k, l, and m, we would arrive at n again. N is both square and cube. And this gets us to what we wanted to prove. We wanted to prove that b is a square number, that c is a cube number, that f is both square and cube, and furthermore, that the consecutive cubes, or the consecutive squares, are separated by one number, they leave out one. The consecutive cube numbers are separated by two numbers, they leave out two. And the consecutive numbers that are both square and cube leave out 5. They are separated by 5 numbers, and we've just proved that, so we're done with the proposition, therefore, etc., Q, E, D. This is one of the most important propositions of Book 9. You'll see this used quite a lot throughout the proposition, so it's important to understand this. And I think it's conducive to understanding to give a particular example. So if we were to begin from the unit, we would obviously start at 1. The simplest continued proportion of this sort is just the powers of 2, which you might already know. They go 1, 2, 4, 8, 16, 32, and 64. And I'll stop there. So what this proposition tells us is because this is a continued proportion beginning from the unit, beginning from 1, the third number will be square, the fourth number will be cube, and the seventh number will be both square and cube. And furthermore, that all consecutive squares are separated by one number. All consecutive cubes are separated by two numbers, and all consecutive numbers, which are both square and cube, are separated by 5 numbers. Do we see that play out here? Well, our third number, or our third term in the sequence, is the number 4. 4 is obviously a square number, it is just 2 squared. So we see that our third number is square. What about our fourth number? Is that cube? Well, 8 is obviously cube. It is 2 cubed. What about 16? Is that a square number? Well, yes it is. We know it's 4 squared. And we notice that between the two square numbers, 4 and 16, there is one number between them. Or in other words, they leave out 1. Next, we would arrive at 32. Well, it's the 5th number, and this proposition doesn't tell us anything about... Sorry, not the 5th. It's the 6th number. This proposition doesn't tell us anything about the 6th number, so we Right now, we won't say anything about 32. What about 64? Well, it's the seventh term in this sequence, right? 1, 2, 3, 4, 5, 6, 7. So 64 should be both square and cube, and it is. It's equal to 8 squared, so it's a square number, and it is equal to 4 cubed. So it's obviously also a cube number. So you see that this proposition holds, and we can continue this proportion as long as we want. We can continue the powers of 2 up to 128, 256, 512, 1024, 2048, 4096, and so on and so forth. This proposition will always hold. It'll tell us where the square numbers are, where the cube numbers are, and where the numbers which are both square and cube are. To put this in a more general way, using any number, we can generate a continued proportion beginning from the unit in this way. We would begin at 1. Our first number would be a. Then we would go to a squared. It's more obvious that the third term is a square number when you do it in the more general way. Actually, I'll write this a bit bigger, just so it's easier to see. The general way you do this, you would start like this. And then the third term would be a square number. That's easier to see if you write it in general notation. And then the next one would be a cubed, and you might already be able to see the pattern because this is technically a to the 1, and even 1 you could count as a to the 0, but that might be a little weird. And we would continue increasing the power by 1 between each consecutive term. Like this, and we would continue on with a to the 7th, a to the 8th. This is generally how you would generate a continued proportion beginning from the unit. And from this, it's easier to see that this proposition holds. The third number, a squared, is obviously a square number, and between each square number, or in other words, between each number that has an even power, right, 2, 4, and 6, a to the 2, a to the 4th, and a to the 6th, those are all square numbers, and they're separated by one number between them. So between a squared and a to the 4th, there's a cubed, and between a to the 4th and a to the 6th, there is a to the 5th. We also know that the 4th number is a cube number, and between any two consecutive cube numbers, there are two numbers between them, so let's see if that holds. Well, our first cube number is a cubed. That's obviously a cube number. We skip 2, we get to our next cube number, a to the 6th. And generally, any number whose power is divisible by 3 will be a cube number. There's a funny way of saying that. All numbers whose powers are 3even are cube numbers, which is just a delightful word. I really like 3even. I think it should be normal, but that might just be me. So we see that between each consecutive cube number, there are two numbers that lie between them, and we can continue that pattern out however long we want. We also notice that the 7th number is a to the 6th. A to the 6th is both a square number and a cube number, and that's more easy to verify in the general formulation because you can split this apart into two ways of writing it. You can either write it as a cubed, take that squared, or you can write it as a squared and cube that, because the order of exponents is commutative. So you can either write a to the 6th as a cubed and square a cubed, or you can write it out as a squared and then cube a squared. Either way, you would get a to the 6th. But from this, it's easy to see that the number 6 is both square and cube, because you can represent it as a square number and a cube number. You can also verify that from the power. 6 is both even, it is divisible by 2, and it is 3 even, it is divisible by 3. So it's going to be both square and cube. So that's all we got to say about this proposition. It's very important to know how to generate continued proportions beginning from the unit, specifically the power of 2, so 1, 2, 4, 8, 32, 64. That one comes up a lot. It's very important to the last proposition of this book, and you'll generally see it a lot in mathematics. I mean, it's the basis for binary, of course, because it's just the powers of 2. So yeah, this is a very good proposition to know just offhand. That being said, I'll end the video here because I have nothing more to say and move on to proposition 9.9.